Thank you. So as Adrian said, I'm going to be talking to you today about using neural methods for compression. And in particular, I will be talking about image compression, which you can think of as a way that can be extended into residual compression. So it could be applied into video in that way. But I think the tools that I'm going to be talking about today are just general. It doesn't really matter what type of media we would like to compress. It will work for pretty much anything, including arbitrary data. Right. So I'm going to first talk about this neural compression business, what we would like to get out of it. I will give you a review of the state of the art in neural compression. And so I'll be talking about some opportunities for using this type of methods, perhaps in video and image encoding. And I would like to start by saying that I think we are at a very interesting point in time because a lot of the things that need to work have started to work. So we are better positioned than we have ever before to use neural compression tools and essentially be able to integrate some in many different ways. So for example, they could be integrated in existing codecs, they could be run standalone. But my point of this talk is to just expose you to some of these ideas that have been developed in this field and see whether you can find something that's interesting and that you would like to use. So the first question before we talk about using neural networks for compression is, why would we ever want to use neural networks for compression? I have been working on this since around 2014. And before starting working on compression with neural networks, I had seen neural networks do very well in other domains. So for example, in classification, they basically ended up being the best methods starting around 2012. And they had been applied to many other domains increasingly more efficiently. And in general, whenever somebody took neural networks and applied to a particular domain, they ended up with state-of-the-art results. So it was very tempting to say, hey, let's just use neural networks. We'll get some state-of-the-art compression tomorrow. Turns out it didn't quite work that way. Nonetheless, it was very exciting at the time. Hardware was available finally that would allow us to train these neural networks quite efficiently. So it seemed like a good time to start. Now, what would a neural codec look like? In principle, a neural codec would consist of a computational graph. Imagine a set of convolutions, additions, subtractions, whatever, and a set of weights. Now, this is very interesting from the standpoint of the following sort of concept. Imagine if you have a program today and you load it in 20 years from now, and you would like to open an image that was compressed with a neural network 20 years from now, and it would be able to decode it, because the codec itself would be just a specification. It would just be able to download the computational graph and the weights and execute it, and therefore decompress that file. So I think if we think about codecs from this standpoint, it's very, very interesting, because any file could just provide a link to the computational graph and the weights needed to decode it. And then it would be a matter of executing it. So pretty much any number of codecs are possible to be implemented using this framework. Now, let's do a quick review of what was happening in neural compression before 2014, when I started working on it. So it turns out, before the AI winter of the mid-90s, there was a fair bit of work that was happening. And in fact, this paper from 1989, so one on the left of the screen, has a structure which is very interesting, because the way they've proposed to implement it was to have an image transform, quantizer, some kind of arithmetic coder, which would essentially do the compression. We would have a decoder and a reconstruction and some inverse transform. And in fact, a lot of my talk today will probably be very familiar once you looked at this particular image, because we would be reusing a lot of these concepts that were developed for neural networks in the 80s. And in fact, if you look at standard codecs, they pretty much mirror the same structure, except that perhaps you have some additional bells and whistles like predictors and so forth. So I just wanted to point out that this existed since the 80s. The only problem was it wasn't actually working. The results that were being published at the time were compressing one image. And I'm serious, like the entire paper was revolving literally one image being able to be compressed. So there was no demonstration that this could work in an arbitrary scenario. And it took very many years until this was possible. And it was mostly because all these methods were so expensive and the hardware at the time was so slow that they just couldn't afford to do it. Now, let's discuss about some goals for neural image compression in this case. I think if this field is to be taken seriously, it needs to provide some methods which are competitive with classical compression methods in metrics that classical compression methods people care about. So it shouldn't be some arbitrary metric that we develop for a particular paper and yes, we're better in that metric. It should be something more reasonable, like PSNR. And as a result, we'd like to have methods which achieve better rate distortion trade-offs than current state of the art. We would like to be able to have methods which are reproducible, meaning if I encode an image on my desktop, I should be able to decode it on my phone, for example. That would be really great. It turns out it's hard. It should be able to run on mobile devices. And ideally, in addition to this PSNR business I talked to you about, they should be able to optimize for pretty much any metric we throw at them, because the methods themselves are differentiable. So if you have a differentiable objective metric, they should be able to optimize for it, whether it's a perceptual distortion metric or not. This is first post-AI winter compression papers I'm aware of. We started working on it back in 2014. And basically, it was a method that promised to do everything. And in fact, it promised to even replace things like arithmetic coding. And as you might know, arithmetic coding is pretty hard to replace because it's a very compression-specific method. Whereas this paper, the purpose of it was to take the entire compression framework and sort of replace it with a single recurrent neural network that would learn how to achieve actual compression, how to minimize bitrate by itself. And in this case, it was a stack of recurrent units. We had a binary quantizer and a stack of recurrent units as a decoder. It was a progressive method. It could achieve variable bitrate by putting more data out, meaning more iterations. So it pretty much sounded like we achieved our ultimate goal, because actually it turns out this is also reproducible across hardware platform. But I would like to argue that actually it was very far away to having achieved this ultimate goal of compression. I think it was too ambitious. As I said, it was trying to replace arithmetic encoding. It was trying to replace the transforms. It was trying to replace everything with a very elegant framework, which would consist simply out of recurrent units. But it turns out it was probably too computationally expensive to be applicable in practice. I mean, it was a nice sort of method that we can look at now and say, hey, it has these desirable properties, but it doesn't have the speed property. And also, it wasn't really competitive with state-of-the-art at the time. It was better than JPEG, which was a pretty big achievement for the time, because nothing had been better than JPEG. And I'm talking about JPEG 90 here, not JPEG 2000, before using a neural method. So now let's move forward in time and kind of discuss what is the actual state of the art in neural networks today. And I'm going to start by discussing the fact that when you look at neural network approaches, we talk usually about end-to-end approaches, meaning you go from pixels, you end with pixels. But we could also be talking about things like learned transforms or specialized entropy models, which could be used to achieve better efficiency in arithmetic coding. And I will be focusing mostly on end-to-end approaches for most of this talk. As I had promised in that first slide with neural networks from the 80s, we are back to the same paradigm, meaning we have an input image, we have some sort of an encoder, which is a bunch of transforms. We have a quantizer, and the output from this quantizer will go to an arithmetic encoder, which creates a bit stream. In order to decode it, we'll use an arithmetic decoder that pushes everything to a decoder network, and we have a reconstruction. Now, what is interesting here is something on the far right. This is the stuff that was missing from the 80s, the entropy model. It turns out when we train these networks, we would like to optimize for the ultimate objective. And the ultimate objective is rate distortion trade-off, meaning rate plus lambda times distortion. And using this framework, it turns out it's possible to obtain exactly this equation and optimize for it. And this factorized entropy model, I will get into a bit more detail, is crucial. This was something that the people in the 80s just didn't think too much about. But in order to make everything work, we really need that. And also, I would like to mention that during training, we cannot backprop through arithmetic coding. So that AE and AD blocks disappear. So we actually pretend we don't do any encoding during training time. We just put the output of the encoder to be fed into the entropy model, and we add noise and feed it to the decoder to be able to achieve compression and train for it. Now let's discuss a bit the entropy model. So the entropy model in this work was the simplest possible imaginable entropy model. So there are a lot of simplifying assumptions. So first off, the output of our encoder will output a three-dimensional tensor. That means you're going to have some width, some height. That will be a fraction of the image dimensions. And you're going to have a bunch of channels. This could be the, let's say, equivalent outputs of filters, except that we now have a stack of convolutions that are producing these outputs. And we're going to assume that every channel is independent from the other. Of course, in practice, this is not entirely true. And in fact, there's a lot of correlation between channels. But we're going to assume something even crazier, that there's no correlation spatially between the points in the image. And of course, this leads to non-optimal performance for compression, but nonetheless, the paper I had just mentioned actually achieved extremely good performance for its time by making these very crazy simplifying assumptions. In the follow-up work, basically this assumption has been relaxed. And in this case, there was this question of, okay, so how do we get these spatial correlations? How do we get an entropy model that is aware of space? What if we could predict for every location in space the standard deviation of a Gaussian and use that Gaussian now to encode the symbols for that location in space? Well, if we could do this, of course, we could get better rate distortion trade-off since the previous slide, because this is strictly more powerful. But it raises a question. How do we store this information? How do we store these sigmas for these Gaussians? Don't we have to pay something to store this information? And of course, the answer is yes, we have to pay some price. But if we're clever about it, maybe the price we pay will be absolutely minimal. So Now let's look at a model which combines the idea from the first slide regarding this autoencoder setup with this idea of a hyperprior, so part where we predict a standard deviation for every location in an image. So the part on the left is just the standard autoencoder. It's literally the same thing, no modification. The modifications that appears is this stuff on the right, which in essence is nothing more than another encoder decoder setup. It's just that in this case, what we're trying to encode are the signals coming from the original encoder of the autoencoder, bypassing the quantizer. And what we decode are not pixel values, but rather standard deviations for Gaussian model. And if you are wondering what kind of network is it, it's actually nothing fancy. And I'm going to be describing the full setup. And in fact, everything you see in this slide is enough to fully specify a compression model that performs close to state-of-the-art today. So what we have is an input image, stack of convolutions followed by some nonlinearities for the encoder. If you look at the figure, there's an arrow going down. That means that we have a stride of 2 that goes down in spatial resolution. And so nonlinearity is something called generalized divisive normalization. I will not get into details regarding it in this talk, but I will tell you that it is a nonlinearity which is learned. So it's in some sense another convolution. And it tries to use the correlation between channels. So it will explicitly try to model this correlation. So the output of GDN is conditioned for every channel by all the other channels. So yeah, it provides a pretty good boost to the signal flowing through this network. Now, as we move on to the right, the output of this encoder goes through these nonlinearities, and before the quantizer, we actually don't use any nonlinearity. It's just a normal linear layer. And we feed this to the encoder of the hyperprior. And this one is much simpler. We don't have to have any special nonlinearity. It's just rectified linear units. And the reason for it is because rectified linear units, which essentially output 0 if you are below 0 and output your value if you're above 0, are very good in classification problems. And what we're trying to do here is predict essentially the standard deviation. So it turns out this architecture works really well in this scenario. So again, we go to a quantizer here, and when now we go up, we need to increase resolution. So what we're doing is we're using something called up convolution, sometimes misleadingly called deconvolution, or a fractional strided convolution. You choose how to call it. It basically is the opposite of convolution. So convolution with a stride goes down, this goes up. And in practice, it gets implemented as the backprobe function for convolutions. So we have this stack of things which predicts the sigmas. These sigmas get used to encode the quantized codes coming from the original encoder. And we have a small problem, and the small problem is how do we encode the bit stream for this secondary encoder? And we can use a factorized prior, again, making those very simple assumptions. Everything is independent. So we can use maybe a histogram or something to encode it. Now, as I said, you are assuming a 0 mean throughout this entire time. There is no reason we should assume a 0 mean. In fact, we know that the codes coming out of the encoder are not centered around 0 for every channel. So it makes sense to also predict the scale when we have this entropy model. But what makes even more sense is to try to have a context model. So context models, of course, are absolutely crucial if you want to get spatial correlations right. Context models also have been sort of very difficult to implement in neural networks. And the reason they're difficult to implement is because you're introducing a serial step in an otherwise fully parallel system. So if we didn't have a context model, pretty much everything you saw in these diagrams can be run in parallel, one stage at a time. So, whereas with a context model, you are trying to predict something. You're going to use this prediction to decode the next bit of information, and then you're going to have to predict again. So it introduces this very expensive loop. So we expect the context model will give us a lot of performance, but we also expect it to slow us down if we do it. So let's look at sort of the performance gains by using these things. So first off, this is the first and only plot with PSNR and bit rates that I will have in my talk. So let's discuss it a bit. So first off, that line on the bottom, so once it's not really visible, it says JPEG. So pretty much every other method on this diagram is better than JPEG, which is really great news. The line highlighted as iClear 2017, that is a model with also simplifying assumptions that I was telling you about, in which, okay, everything is decorrelated. We don't care about any correlations. So as you could see, there's a pretty good jump, and it's finally beating JPEG 2000. And the highest sort of line on this graph is this Hyperprior plus context model that I was describing. We saw a huge improvement in just 1 year by switching to this model. So that was some pretty amazing jump. If you're curious how would HEVC, for example, fare, that's the line below the top line. And as you can see, well, obviously, it was surpassed by this Hyperprior model. So it's very encouraging because for the first time that I'm aware of, there exists a method that's fully neural that is now competitive with what was at the time state of the art. And just to illustrate this visually, let's look at JPEG at 0.15 bits per pixel. Actually, other methods will not be at 0.15, they will be at lower bitrate. But this was sort of the lowest bitrate for which JPEG wasn't producing essentially a grayscale image. Now, if you look at BPG, which is basically the HEVC iframe, it looks way, way better. It looks like completely from a different generation of codecs, as you would expect, at a lower bitrate. This is what one of the neural methods is doing. So I'm going to switch back and forth between the two. I don't think you'll be able to notice the difference, but I will explain what happens. So there are fewer details with the neural method. So this was a method which was assuming a zero mean Gaussian for modeling the distribution of symbols. So the question becomes, okay, so if this loses detail, of course, it's not as good as BPG. So what about this context model business that I was describing? Well, so the details actually come back. So I'm going to, again, try to switch between the two. So a lot of the details which are lost when compared to BPG now can be seen actually here. And I would argue actually it looks in general sort of more pleasing to the eye perhaps. This particular version was optimized for mean square error. So it's in the same sort of class of optimizations that BPG was tuned for, which was also mean square error. Now, let's discuss something which perhaps is convenient to forget, and that is determinism. So if you are familiar with entropy models, your alarm bells should have been triggered when I was telling you that we have a neural network that is predicting distributions. Because these distributions, even though we parameterize them by a mean and a standard deviation, they're very finicky. And what that means is if we make a mistake in predicting this mean or standard deviation for the distribution, we could get, we could get into some very bad scenario. So we need to have a way in which this highlighted part here of the model is fully deterministic. So regardless of what platform to run it on, I would like to get the same numbers out. Now, neural networks in general run in floating point. Floating point is a wonderful thing, except for the fact that it's not fully standardized everywhere. And to add sort of insult to the injury in the face of floating point and neural nets, different vendors might choose to implement certain things differently. So for example, you have different ways of optimizing a convolution, which might produce slightly different results. And if a vendor chooses to do that optimization, we cannot get the same number on that platform as we got on our training. So this is a very scary prospect. And let's see what does it actually do in reality. So here is our original image that we compressed on a CPU, and we decoded it on a CPU, the same CPU, but with a different number of threads. It turns out you don't even have to change vendors to get this kind of problems. Because if you have multi-threading, it turns out when you accumulate floating point values, depending on the order in which you accumulate, you might get different errors. So in a multi-threaded environment, there's no guarantee on which order your accumulation will happen. So as you can see, neural methods seem kind of doomed from this standpoint. So what can we do about it? How can we save them, shall we say? So first off, only the entropy model are affected by this problem. If you have this kind of errors inside the autoencoder, it doesn't matter. Your image won't look exactly the same, but you won't be able to perceive. Maybe 1 pixel value will be off by 1 or something. So it doesn't matter. So as long as we can get these entropy models right, we're good. So let's talk about factorized model. So in the factorized model case, we can take our models that we trained with. We can compute the lookup table out of it and save it. And we can do this in integers, avoiding floating point altogether. If you do this, we have the first sort of autoencoder paper completely solved. No issues there. But now, how do we deal with these more complicated entropy models? Well, they consist of convolutions plus rectified linear units. We know that this decoder and encoder need to agree on what was used. So whatever we use during training has to produce exactly the same results as it will be produced from that point on. So any mismatch of any kind will yield to some catastrophic decode failure. So we need to worry about making convolutions and activations completely deterministic. Now, integer is the answer. So we would like to have integer convolutions, ideally, supported across all platforms. It turns out today they are not. Most frameworks will not support, in fact, integer convolutions. So in order to make it work, we need to fake integer convolutions. And one way to fake them is by using floating point 32 and essentially quantizing to the nearest sort of 8-bit threshold. We pretend we have an 8-bit machine. And this tends to work reasonably well, even when you go, for example, on ARM CPUs or NVIDIA GPUs and so forth. And we also need to do some tricks which would kind of keep track of ranges and do scaling and so forth. I will not get into too many details, but We do have a published paper if you're interested, and it will be referenced in the references that gets into a lot more detail. And with respect to the activations, well, because we want to quantize, we are going to get this kind of step function behavior from our activations, which perhaps might sound scary because, well, you're losing precision, your performance potentially will go down the drain, and so forth. It turns out it doesn't change our performance almost at all. So it's a very good news. Even if we do this effort to make sure that everything is quantized, everything is cast to integers, and we introduce a lot of overhead, in the end, actually, it doesn't matter. We have the same performance. And this is super important because we typically will use a different platform for training these networks than we would be using, for example, in day-to-day use. We would like to train these things on tensor processing units. We would like to train them on GPUs. So it's very advantageous from our own time, the developers, to try to use these platforms. And making sure that everything runs on CPU and mobile is absolutely mandatory, essentially. Now, speaking of mobile and speaking of speed, let's discuss this additional item. So if you look at 2016, which is when we ported our first neural network for compression to mobile, we were using, I think, a Nexus 5 at the time. So this benchmark was run on Nexus 5. We were decoding 500 pixels per second. So there's no megapixels, that's literally pixels. It doesn't sound very fast, I think. So let's see how it changed over time. So when we kind of switched away from this recurrent model, we saw an absolutely incredible jump, basically. We are now on the y-axis, instead of pixels, we have megapixels. So we are reaching close to 6 megapixels on a phone. And let's look a bit at some other speeds of the same model. So when we run on a Pixel 3, which I think is a Qualcomm 845, we get about close to 6-ish megapixels. If you run on a CPU on my desktop at work, I'm getting about 16 megapixels per second. And if you run on a Titan XP, it's an NVIDIA GPU, we get about 40 megapixels per second. So as you can see, we can get models which can be quite fast. And in fact, speed has been kind of one of the things that we were really worried about, and we wanted to make sure that these things are feasible. So we investigated how to speed these things up, and it turns out that it's possible to maintain PSNR. So on the x-axis, we have PSNR, and on y-axis, we have computational teraflops. So, sorry, flops, not teraflops. So how many flops does it take to achieve that PSNR? So for example, at around 30, you can see we can have basically factors of 1,000 difference in compute to achieve more or less the same point in PSNR. Now, of course, we would have to do this for every point on the ray distortion curve if you want to be truly optimal. So there's quite a bit more work to be done. But I haven't talked yet about something else, and that is everything that we are doing is more or less related to the computational requirements of our autoencoder. That's where your compute is. The entropy model, despite being a neural network, accounts for maybe 2% of runtime. So if we can get the autoencoder to be fast, this is what our bread and butter is. So we can trivially get it to be 2 times faster than whatever I just shown by going to floating point 16. And it turns out we ran this experiment and we saw no loss in distortion. So it's the same distortion, you just get 2x faster. Ideally, we would like to be able to run the autoencoder in 8 bits, because technically this could improve the speed by another factor of 2, getting it to 4. And also, the numbers I showed on mobile didn't use GPU at all. It was purely CPU. Now, let's talk a bit more about opportunities and kind of where this compression is outside of Google as well, because most of the work I have described thus far was basically done within our group. So in order to incentivize research in the area, we started a challenge on learned image compression with the explicit goal of encouraging researchers to develop methods that are learning-based, ideally with neural networks, and also to expose them to good practices. Believe it or not, the idea of having to generate a file, reading said file from disk and decompressing it was quite foreign in 2018 to most researchers in this area. So we made it explicit as part of our challenge that you give us some files and a decoder binary, and we'll decode these files for you on a different machines than what you had to encode, because we'd like to test this determinism problem as well. In this challenge, we had about 330 images. We were asking competitors to compress them to an average of 0.15 bits per pixel. And in the first edition of Click, which was in 2018, 60% of participants used VVC or some other derived technology, like maybe H.265 sometimes and so forth. So from the standpoint, it was just showing that the field is just not very mature because, well, there aren't that many different compression algorithms available. But we actually ran this in 2019 as well. And we saw a huge increase in terms of methods that are purely neural or that had a neural component. And in fact, this business of Hyperprior has been the most popular methods that people have derived from to make improvements. And if you look at the breakdown of what types of methods participated in this year, we ended up having about 44% being purely neural end-to-end, about 40% being existing codec plus some neural network to enhance it, and about 11% were just perhaps VVC or H.265. Our evaluation was done both using metrics like MSSIM and PSNR, but also human eval. And for human eval, we wanted to evaluate every single method, but we would like to get a more accurate ranking of the top methods. So in fact, the highlighted methods here have been fully evaluated by humans, whereas all the rest had maybe a few images evaluated by humans, and if they were just too bad, we didn't consider some for eval. What is interesting is to look at the two types of highlights. We have a blue highlight and a yellow highlight. I hope it's yellow. Sorry, I'm colorblind, so I'm not sure. But I hope it's yellow. Anyway, I'm going to call it yellow. So yellow ones are essentially methods which have been derived from classical approaches plus a CNN, whereas the blue ones are fully end-to-end CNN plus Hyperprior style. And what you might see is that this type of methods tends to favor MSSIM, whereas classical approaches tend to favor PSNR. And I think this is by design. I think people designing VVC, H.265, and so forth optimized as much as they could for PSNR. Whereas people who have been developing the neural network approaches perhaps optimized for a mixture of PSNR, mean square error cities, and multi-scale structural similarity, and so forth. So we have a difference from this standpoint. Now, what about comparing visually the winner of this year's Click to one of the baselines which we had? So BPG, again, HEVC, iframe. I'm going to switch between it and the winner. I have no idea. No, sorry, you can't see it. So I'm going to have to describe what's happening here. So on the man's face, BPG basically loses all texture. It's as if he doesn't have a skin or forehead. So it's quite jarring to look at it. Also on the woman's eyes and face, they tend to get a bunch of artifacts from BPG, which completely disappear in the neural method. And I'm showing it to this just to understand the evolution of these methods. Like we were back in the 80s where it was completely impossible to achieve anything reasonable, to early 2000s when we had the recurring methods that was beating JPEG finally. And now we have this where I think there is no question which method in this particular case is better. So let's discuss now about these ideas and kind of using ideas from neural compression to improve classical compression. So I had talked about building blocks. I had talked about transforms. So for example, the convolutions, you can think of them as some types of transforms that are learned. We tend to learn some in neural compression end-to-end, but there is no reason we couldn't learn some for reconstruction, such as like DCT. Additionally, we had this generalized divisive normalization block, which is also learned. And this could be applied on top of existing transforms like DST, DCT. It doesn't matter which transform. It will help it decorrelate better its channels if they are not already there. So you can think of maybe using this idea to improve an existing codec by throwing GDN on top of an existing transform. I also talked about entropy models. So of course, all these entropy model ideas that I have discussed can also be applied to an existing codec because it's in the end a matter of predicting symbols. And neural networks tend to be very good at this. And we can do this in an autoregressive manner or not autoregressive, perhaps it's too slow. But maybe if you do it at a coarse enough level, it's still fine, or predicting many symbols at once. There are other methods that I would like to encourage you to look into, such as integer discrete flows, which by their very nature use integers. So they are safe from a compression standpoint, and they allow you to model distributions very nicely, very complicated distributions. And of course, we can also look at using ideas from classical compression methods and putting them into neural networks. So you might have seen I have not uttered the word, let's predict a patch using some context. I never said that. Well, that's because it's typically not done. But even so it's not done, it could be very interesting to try in a neural context. It could be very interesting to use autoregressive methods based on simple heuristics. So, for example, you could say, I'm going to predict my next pixel as a linear combination of my left and top left, or something like this. And this could be something really cheap. But maybe we could have hundreds of these predictors and encode which one was actually useful for predicting the next value and encode that in the bit stream. So these types of stuff that are quite sort of typical, I would say, are simply not explored in the area of neural compression. So I really think it would be cool to insert some of these into the field. And of course, because I've been working on fully neural approaches, I also would like to pitch sort of maybe having a codec that's a fully neural codec. And the reason is it would be super flexible. As I hinted in the beginning of the talk, you'd be able to describe this codec by a computational graph and a bunch of weights. As long as the format of this descriptor doesn't change, you'd be able to use an app from today, 10 years from now, decoding the latest format. You'd be able to get files which have been compressed with domain-specific compressors. So imagine the following. Imagine that you would like to compress images of, let's say, MRIs. MRI images look very different than natural images. So you could have an entropy model that was trained on MRI images. You could have transforms which have been trained on MRI images as well. So you could do suddenly a lot better without having to change the underlying piece of software. You would just change which model you used. And additionally, something I haven't discussed explicitly in this talk, but it is possible to take this very expensive autoencoder business and start messing around with it. And for example, you could have a neural network which was trained for image compression that's extremely high performant but expensive. But you could say, I'm going to provide a cheap decoder, because it's in fact possible to have a special decoder that's trained to be very cheap computationally, that will produce a worse distortion performance as the original one, but might run 10,000 times faster. So you could do this type of stuff, for example, for previews. So I really think it's basically boundless what kinds of stuff we can do with these neural networks. But of course, not everything is clear. Like if it were clear, I wouldn't be here. We would be trying to launch something based on this. So how can we guarantee that this model that I was pitching to you will work 10 years from now? I was just telling you it will work 10 years from now. Well, ideally, the entire pipeline would stay stable, and we would standardize on a pipeline. So in order for this to happen, a standard must be made, and it must be maintained over years, and must have certain guarantees about what kinds of operations are available, how they should be implemented, and so forth. Another thing is, if we would like these types of codecs to be widely deployed, they should be fast regardless of platform. As I had shown you, they can be fast depending. I mean, if you have, for example, a Titan XP video card, it's probably already fast enough. You should have no problem running it. But if you have a mobile, maybe 6 megapixels per second might not be fast for you. Maybe it is. So it's not clear if we are there yet with the speed. Also, if we are going to depend on TPUs or neural processing engines, they might not be deployed everywhere. There are some power efficiency concerns. So, for example, when you have a video decoder chip, you're pretty much worried about how much power it will use when it decodes video. So these are things which are not within my power to decide or develop. It's something that the community has to figure out, whether these things are power efficient enough. Another thing is, how do we do multiple bitrate? In the autoencoder model setup, you only get one rate distortion trade-off. You saw a curve, right? I showed you a curve. That was composed out of many models. So, for example, 5 or 6 models. Recently, there's work by Choi et al., who are not from Google, they are from Samsung, that's presented at ICCV, which essentially takes this hyperprior model that I was discussing and they make it multi-rate, which is very promising because they don't seem to lose much performance when making it multi-rate. But I feel like there's a lot more research to be done here on how to do this. So I think there are a lot of open questions, a lot of areas for research. I think we could try to learn between these two fields. As I said, there are learnings to be had both directions. And with that said, I would like to make sure that you know that I actually put a set of references for you here if you're interested to dive deeper in any one of the methods that I have described. And the bottom link there is a challenge on learned image compression. It's a website of the challenge. We're going to try to run it again next year. So I would like to invite you all to also try to participate because, as I said, VVC was the most represented codex there, and it would be great to have more diversity there in terms of codecs. And lastly, I would like to make sure you know that we developed an open-sourced bunch of libraries that should enable you to do experiments with neural compression methods if you are so inclined. And in fact, this hyperprior business that I was discussing is already on that website. So if you'd like to, try different things, you are more than welcome to clone this repo and go from there. So that's all I have. I would like to have any questions if you have any.
Yanis just beat you. Thank you. Can you give us a order of magnitude? How big are the models right now? How many megabytes? Or?
Yes. So depending on architecture, you could be looking at a 1 megabyte, 2 megabyte model, or maybe 10 megabytes. It all depends on, how many parameters you want to have in the end. So as I showed you that compute chart, it's possible to achieve the same thing with far fewer parameters. So.
Thank you.
Question on when you were over here, when you were competing with a BPG, what were the GOPS or gigaflops that was used by the Hyperprior?
Okay, so I cannot tell you because we never measured that part. However, we know that when we benchmarked the models trying to see where the bottlenecks are, it was always the autoencoder. So the Hyperprior was a few percent, very, very small percent of the total compute. So the entropy part was actually the cheapest.
But for example, to achieve that result, was it 1x, 2x, 4x, 10x the computation?
Okay, I see. So I cannot speak of BPG because I don't know how to compute flops for it. But it depends on image size in the end, right? Like it depends on what image, because you see, you have to see every pixel in the image, right? And for every pixel, you have a certain number of flops. And I don't know exactly how to compute some, but if I go back to see computational slide, maybe we can look at the y-axis to see. Okay, so we are talking about 10 to the 6 flops for this particular image. I don't know what image it was.
Per pixel?
No, it says for the entire image.
For the slices.
Yeah, I understand it said that, but it was a mistake. I think. Sorry, email me after this and I will confirm, because I didn't do this work. It was Nick Johnston who did it, and I can confirm with him.
Okay, so that's 10 megaflops?
Yeah.
Okay.
Okay, so it's probably per pixel in that case.
Yeah, okay, thank you.
So in hybrid encoding architect, there are 2 encoders. One is image encoder and one is hybrid encoder. So I'm wondering, given a certain bit budget, how do we decide the bit allocation between those 2?
This is an excellent question. So the way we do it is we let the neural network figure out the allocation. We have essentially our loss is rate plus the hyper rate plus lambda distortion. So basically we treat how much information we put in the Hyperprior versus the regular stream in the same manner, and the allocation happens naturally. Like we don't run any optimization after the fact, just during training. Let's go for this one first.
Check.
We'll go over that. Sure. You can go next.
Oh, sorry. Have you explored model pruning?
Yes, of course. It turns out it's harder in this domain because of the activations that we have. So those GDNs, they make every channel depend on every other channel explicitly, so we can decorrelate. So you will never have a zero activation. But we are working in architecture search, and there will be a paper by Nick Johnston, which is essentially this graph that I'm showing you to right now. It kind of discusses what we did and what worked.
Cool, thanks.
Yep.
Hi, yeah. So I had a very question on if you can give a rough idea as to how much of the gain comes from the nonlinear transform part versus the Hyperprior part. So suppose you didn't have the Hyperprior, but only use the best possible adaptive entropy coder for the bits in the bottleneck. After the bottleneck, then how much would the difference be?
Right. So our Hyperprior, of course, is a form of more efficient encoding of the latents. And what you're asking is, what if we took an adaptive encoder for the latents and used that instead? We didn't explore, for example, having a custom one made we went and looked at stuff like zip, for example, with gzip, bzip2, Brotli. And what we observed is that it doesn't get much better than the line which is labeled iClear 2017. It's very interesting. I think it's just a matter of making that predictor more powerful and adapted to this domain.
Thank you.
Yep.
I'm just wondering how much of bit rate is spent on coding the Hyperprior, and if it's high, like, do you think it's compressible? Can we have maybe a Hyperprior for that?
It's a very, very valid question, actually. So because we are using a weaker entropy model for the Hyperprior, if we spend too much on it, we could put another Hyperprior on it. And in fact, there's a work by, I think, Fabian Menzer and Augustsson, who have done it for lossless encoding of images. They're essentially using the Hyperprior as a lossless encoder, and they stack them up. Now, in terms of actual ratios, I think we are talking about less than 5% is spent on the Hyperprior information.
Thanks.
Yeah, here. So I have a question about the role of GDN. I think maybe that's what Deepak was asking.
Mhm.
So what happens if you just replace the GDN by, common nonlinear and keep the rest?
That's a very, very fair question. And the answer is we would suffer a drop in performance of a few percent, maybe 5%, something like that. It wouldn't be a deal breaker. In fact, our fastest models drop GDN just to make it more compute efficient.
I was trying to understand, do you think the GDN is really trying to make all the feature maps independent of each other?
This is our current guess, yes. So that doesn't happen with ReLU, for example.
Thank you.
Thanks for the presentation.
Yeah.
So I have a question. So the model parameters are quite big for different bit rates and to train them, right? So I was wondering if there is a subset of a network there which could act as a backbone for training as well as for storage, and so that you don't need to store all of these model parameters. Did you explore in that?
That's an interesting question. We were looking at this from many angles, including saving part of the network in a file, for example. I don't think we have any promising results there yet. So basically storing a delta from a model, for example. But yeah, it is an area that we are actively looking at. In fact, we have some work on model compression itself that uses ideas presented in this talk. So turns out you can apply the same idea to compress a neural network with a neural network.
So the codec image set is SDR. Have you tried to use HDR material to see what happens? Okay, or animation?
No, we haven't. It's on the to-do list.
Sure. So it's another question with BPG. Did you enable adaptive quantization, or did you just because you're trying to optimize things in a more subjective way?
In Click we didn't. I don't think we did. When we compare results, we always try to find the best possible parameters for all codecs. So we do a parameter sweep on BPG to generate this graph that we're looking at right now.
Another thing I noticed that for your current test, you're still using 420 BPG, not for this one, but for your, let's say, competition.
Oh yes.
Are you fixing that? Because that was the problem.
Yes, you have a very, very fair point. I think 444 may provide some better results in that context. We felt that, and it's just a legacy thing. So we felt that neural networks in 2018 had a very hard time getting to the level of BPG. And we didn't want to have a baseline that's too hard to beat at the time. So it was designed to allow for more interesting competition to happen. Ideally, of course, now that we know that they can actually do it, we can try to use the best possible BPG optimized image at every rate point. Yes.
Final question. I mean, you're using this only for compression right now, but you could use also machine learning systems, and I think there are contributions, presentations here, as a preprocessor. So you could apply your machine learning to pre-process an image and then use a conventional codec also to code that image afterwards. And of course, you can do post-processing as well.
Yep.
Are you putting that as part also of your
so some click methods will in fact do that. So I know of one that, for example, was producing a grayscale image that was encoded with HEVC, and since they had some side information that they were running Super S through and getting a very beautiful color image out of it. So definitely, I would like to encourage more of this because this kind of combines both worlds, right?
Okay. George, thank you very much.
Thank you.
Really interesting.